Marhaba. Okay, in this session we want to learn a new way to find the greatest common divisor of two integers. Okay, remember we discussed one way which was using the prime factorization of the two integers m and n, and then we choose the minimum exponents of in the two prime factorizations, and from this we obtain the GCD. But the problem with this method is that computationally it takes a long of steps by the computer to compute the GCD. Because where is the problem? The problem is to compute the prime factorization of a number. Computing the prime factorization of a number takes a lot of steps to find these primes which compose the number. So today we want to learn about the Euclidean algorithm, which is a faster algorithm in computing the GCD. Okay, so before stating what is the algorithm in its general form, let me introduce it in an example. So we want to find the GCD of 91 and 287. Okay, so I want to tell you what is the Euclidean algorithm. We want to apply it to find this GCD. So the Euclidean algorithm depends on the division algorithm. We will successively apply the division algorithm. So the first step, so here is step 1. Okay, step 1, divide the larger number by the smaller number. So let's divide 287 by 91. Remember, this is using the division algorithm. So this means that there are two integers q and r, where r is the remainder, and the remainder is bigger than or equal to 0 and strictly less than 91. So q here will be 3 plus the remainder will be 14. Right, and notice that the remainder must be strictly less than 91 and bigger than or equal to 0. Now the next step is the following. So remember, we will divide this word is called the dividend, and this is the quotient, and this is the divisor, and this is the remainder. We will repeat the division algorithm, okay, to divide 91 by 14. So here is 91 is equal to 14. Now we want to find q and r here. So what is the quotient? We will multiply 14 by 6 and get what? 84, and the remaining will be 7. So this is the remainder here, and notice that 7 is strictly less than 14. Right, it should be strictly less than the divisor here and bigger than or equal to 0. Now we repeat this again, and so we will divide again 14 by 7. Okay, so we will repeat, let's divide 14 by 7 plus the remainder. So how many steps of length 7 we need to get very close to 14? It's 2. Actually, we hit 14, so the remainder here is 0. And notice that 0 is bigger than or equal to 0 and strictly bigger than 7. When we get a remainder of 0, we stop, and the algorithm declares that the last non-zero remainder to be the GCD. So here the remainder will, okay, so this is step 2 and this is step 3. So in 3 steps the algorithm computed the GCD, and the GCD, okay, is of 91 and 287 is 7. Okay, this will be the remainder. So I hope the algorithm is clear. Now what we want to do in the rest of this session is we want to prove the correctness of this algorithm, which means why whenever we apply this algorithm, first we will reach a step where we hit 0. So think why 0 will at some point be our remainder in some step. And second, why this number is really the GCD of the two numbers we started with. So we need to prove these two statements. Okay, so let's say what is the Euclidean algorithm in its general form. So the Euclidean algorithm. How does it start? Let m and n be, say, let's say positive integers. Okay, then we want and suppose that n is the bigger one, okay, where m is less than or equal to n. Okay, now what we will do, what is the Euclidean algorithm? It tells us successively apply the division algorithm. So let's see what's step 1 in the general form. Divide the bigger one by the smaller one. So n we will get two numbers, say q1, the quotient, so times m, plus r1, the remainder of the first step. So notice here that r1 should be strictly less than m and bigger than or equal to 0. This is by the division algorithm. Now step 2, what do? We divide m by r1. So we apply the division algorithm again and we obtain, say, q2, and here is r1 plus a new remainder r2, and notice that r2 should be strictly less than r1 and bigger than or equal to 0. Okay, let's see what do we do in step 3. Now we divide r1 by r2. So r1 is equal, now we get a new quotient q3, r2, and a new remainder for step 3, r3. And here, by the division algorithm, we know that r3 is bigger than or equal to 0 and strictly less than r2. I hope you can notice the pattern here is that the remainders keeps decreasing, strictly decreasing. So r2 is strictly less than r1, so r1 is strictly bigger than r2, r2 is strictly bigger than r3, and so on. So we keep doing the steps until, say, let's see what happens in step k. In step k we have that this is equal to rk minus 2. We will divide it with, so here it will be qk and here it will be rk minus 1 plus rk, where rk is bigger than or equal to 0 and strictly less than this one, rk minus 1. And let's say we will, at step k plus 1, here we will have rk minus 1 is equal to qk plus 1, and here we will have rk plus 0. Okay, so I still didn't say why this must happen, but in this case, once we get 0, then the algorithm will declare the first non-zero remainder to be the GCD. So in this case, the GCD of m and n is equal to rk. So we want to see this. So first, why at some point the remainder will be 0? Okay, again, so first observation. So notice that from here we started with m, and m is a positive integer. So m is a positive integer, and then r1 is strictly less than m. So if we start at m, say 100, r1 will be 99 or 90 or maybe 2, I don't know, but it will be strictly less than. Okay, and r2 is strictly less than r1, r3 is strictly less than r2. So m is positive, but r1 is strictly less than m, and r2 is strictly less than r1. And so notice that at every step we decrease by at least 1. So if m is 10, r1 is 9 or 8 or 7, and r2 is 8 or 7, and so on. We keep decreasing, and notice that all these numbers, all the ri's, are bigger than or equal to 0. So all of them are bigger or equal to 0. And so since we keep decreasing, since we have only finitely many integers between 0 and m, and we keep decreasing, at some point we must hit 0. Okay, so here it will be, say this is rk, and then rk is strictly bigger than rk plus 1, and this is rk plus 1 is 0. So this 0 is the rk plus 1. So the reason why we will hit 0 is that m is positive, and at every step we keep decreasing, and which means that at most after m steps we have to hit 0. Okay, now the second point, which is a little bit more unclear, is why this number is the GCD. Okay, I will tell you why now, but we will prove, and then we will prove it. Okay, the reason is that we want to prove that if we have four numbers of this form, and n is equal to q1m plus r1, then the GCD of these two is the same as the GCD of these two. Okay, so the GCD of n and m is equal to the GCD of m and r1. We will prove this now, but okay, believe me for now. So this means that the GCD of nm is equal to the GCD of mr1. And similarly for this, we know that if you write four numbers in this form, then the GCD of m and r1 is equal to the GCD of r1 and r2. So okay, maybe I can write here in green. So from step 1, we know that the GCD of n and m is equal to the GCD of m and r1. This is from step 1. So here I will write step 1 of m and r1. Now from step 2, we know that the GCD of m and r1 is equal to the GCD of r1 and r2. So this is equal to the GCD of r1 and r2. Now from step 3, what do we know? We know that the GCD of r1 and r2 is equal to the GCD of r2 and r3. This is equal to the GCD of r2 and r3. You can see the pattern, so we can continue like this until the last one, which is okay, so this will be equal, all of them will be equal until the very last step, which is here. Look at step k, then we know that it's equal to the GCD of rk minus 1 rk. But I tell you that we know what is the GCD of rk minus 1 and rk. Why? Because look at the very last step. Okay, look at this step. What do we know from this step? That rk minus 1 is equal to qk plus 1 times rk, which means rk minus 1 is equal to an integer times rk. But this implies that rk divides rk minus 1. Right? This is the definition of divisibility. Rk divides rk minus 1 if there is an integer, and in this case it's qk plus 1, such that rk minus 1 is equal to qk plus 1 times rk. Now, since rk divides rk minus 1, okay, then ask yourself, what is the GCD of these two numbers? The GCD of rk and rk minus 1 is what? By definition, it's the greatest common divisor of both of them. Now, the point here is that rk is a divisor of itself, and from here we know it's a divisor of rk minus 1. So this means that the greatest and the common divisor can't be greater than any of these. So this means that rk is the greatest common divisor of these two. Okay, maybe in numbers it will be clearer. The GCD of 6 and 36, since 6 divides 36, then the greatest common divisor of these two numbers is 6. Okay, so here rk divides rk minus 1, so the GCD is rk, the greatest common divisor of both of them. Why? Again, because rk divides rk minus 1. Okay, so if we get back to this, we find that the GCD is rk. But all of these numbers are equal, so this means that the GCD of n and m is equal to rk. And what was rk? It was the last non-zero remainder. Okay, so we explained why this process has to stop and why the remainder, which is non-zero, the last one, must be the GCD of n and m. It remains to explain this. Okay, so let's do a lemma here. Okay, so lemma. Suppose we have 4 integers and n is equal to q times m plus r. So we have 4 integers n, q, m plus r, and if you multiply q times m and you add r, you get n. Then we will prove that the GCD of n and m is equal to the GCD of m and r. So the GCD of these two is equal to the GCD of these two. Notice m is common. Okay, let's prove this. Proof. Okay, let D be a common divisor of n and m. Be a common divisor of m and n. Okay, this means, okay, what does it mean? Let D divides n and D divides m. Okay, remember we proved in the divisibility section that if an integer divides two integers, then this integer d, then d divides, say, any multiple of n plus any multiple of m. Then d divides kn plus lm for any integers k and l. Okay, for any kl in the integers. We proved this, one of the properties of divisibility. But notice now, okay, so we know, okay, notice that r, so notice that r is equal to n minus qm, right? Because we know, and from here we know that r is n minus qm. Okay, but again, this is like the number 1 multiplied by n plus the number minus q multiplied by m. Now, d divides n, right? So d divides n and d divides m. So d must divide any multiple of n plus a multiple of m. So this means that d divides r, because this is equal to r. So what do we know? That d divides r and also d divides m. Okay, this means that, so d is a common multiple of what? Is a common multiple of m and r. M and r. Now, so what is the, okay, note d is a common multiple of m and r. So what is the relation between d and the greatest common divisor of m and r? So here we have d and here we have the greatest common divisor of m and r. Now d is a common, okay, sorry, not a common multiple, a common divisor. My mistake, sorry. It's a common divisor, right? Here, look here, we proved that d is a divisor of m and d is a divisor of r, so it's a common divisor of m and r. Now, this number, denoted by GCD of m and r, is the greatest common divisor, and d of m and r, and d is a common divisor of m and r, so this means that d is less than or equal to the greatest common divisor of m and r. Okay, so what did we do here? What happens is we chose a common divisor of m and n, and d, and we showed that this d for any divisor of m and n is less than or equal to the GCD of m and r, but the GCD of m and n could be d, because it's a common divisor of m and n. Look, d was any common divisor of m and n. The GCD of m and n is a common divisor of m and n. So we proved this, right? Now we will do a similar argument to prove the opposite inequality. So now again, let D now, okay, maybe I have to use K, say, let K be a common divisor of M and R. So suppose K divides M and K divides R. Then K divides any multiple of M plus multiple of R. So then, since K divides M and K divides R, then K must divide, say, Q times M plus 1 times R. Right? This is again by the property of divisibility. But what is this number? Qm plus R is n. So K divides n. So what did we figure out? That any common multiple of M and R divides M and divides n. Okay, so this means, so K is a common multiple of M and n, which means it should be strictly less than or equal to the greatest common multiple of M and n. Okay, but so any common multiple of M and R is less than or equal to the greatest common divisor. What I am saying, sorry. So K is a common divisor of M and R. And then we showed that if K divides M and divides R, then it divides N, which means it's a common divisor of M and N. Since it's a common divisor, so K, so maybe here I say K is a common divisor of M and N. Okay, so since it's a common divisor of M and N, it must be less than or equal than the greatest common divisor of M and N. Okay, so then, but K was an arbitrary common divisor of M and R. In particular, the greatest common divisor of M and R could be one possibility of K. So the greatest common divisor of M and R is a common divisor of M and R. And from here we know it's less than or equal to the greatest common divisor of M and N. Okay. So here we proved that GCD of M and N is less than or equal GCD of M and R, and here we proved that the GCD of M and N is greater than the GCD of M and R. So these two inequalities together proves that GCD of M and N must be equal to the GCD of M and R, which finishes the proof. Okay, so this is this. We proved this theorem. That if you write 4 numbers in this form, then the GCD of M and N must be equal to the GCD M and the GCD of N and M is equal to the GCD of M and R. And we use this lemma. Okay, where did we use this lemma? We used it several times. Okay, we used it in step 1 to say that the GCD of N and M is equal to the GCD of M and R1, and the GCD of M and R1 is equal to the GCD of R1 and R2. So all of these GCDs are equal until the very last, that the GCD of this one, of these two, is equal to the GCD of RK minus 1 and RK. But from the very last step, we know that the GCD is RK. Okay, so this is the end of the Euclidean algorithm. So in general, we just apply the division algorithm several times until we get a remainder of 0, and then the GCD will be the last non-zero remainder.